today's MOX Colloquia. Professor Nick Trefethen, I'm sure everybody knows, but let me spend a couple of words. So Professor Trefethen is the professor of numerical analysis and the head of the numerical analysis group at the Mathematical Institute of the Oxford University. He studied in Harvard and then in Stanford, and then he moved to MIT first and then to Oxford some years ago. He researched, so he made research on a wide range of topics and is very famous for his results on theory and algorithm and software and physical applications, particularly involving the concept of pseudospectra, which I think is really, the concept is due to Professor Trefethen. He's very widely known. He wrote many books. Probably the most famous one is Numerical Linear Algebra with David Bow, which I think, if I'm not wrong, is one of the science best-selling books ever. His research is, and he received a lot of prizes and recognitions for the contribution he gave to many different fields, including the Leslie Fox Prize for numerical analysis, the gold medal of the Institute of Mathematics and its applications, and in 2020 he received the very prestigious John Neumann Prize by Science. So it's a great pleasure to leave the floor to Professor Trefethen, that today is going to speak about applications of AAA rational approximation. Please, Nick, the floor is yours.
Thank you, Paula, and thanks to everybody. So we're in a nice room here. I guess a few people are online, but a number of people in the room I've been speaking with today and yesterday. So thank you all. It's a talk, you could say, about numerical approximation theory. I've spent many years, the last 20 years, really working on polynomials, and that leads to Trefethen. And polynomials also lead to most numerical methods. It's the starting point for numerical computation. But there are problems where polynomials aren't good enough because you have singularities or nearby singularities or unbounded domains. And everybody has known for a long time that in theory, rational functions ought to be powerful in cases like that. But what's been missing is an algorithm for really computing rational approximations quickly and reliably. And it seems that we've discovered that algorithm sort of by chance. Me and Yuji Nakatsukasa and Olivier Sett in 2016, actually, the paper was published in 2018. We eventually found this algorithm that we call AAA, and it's just amazing how it changes the landscape. Suddenly, it's easy to compute rational approximations. And the point of this talk is to show you how you can begin to use that power. So it's not a talk about the algorithm except for 5 minutes. It's mostly a talk about how you can use such an algorithm if you've got it. I hope everyone hears me. Do we have confirmation online? Everybody okay? So I'm not used to sitting down, but I'll do my best. And I've been told to move the cursor when I want to point at something. So here I'm pointing at a bit of code telling you how one calls the AAA algorithm. The point is, it has 2 arguments. Z is a set of real or complex sample points, and f of z is a set of values, data values at that point. So when I call AAA of f comma z, I'm computing a rational approximation to the data f on the set z. And by default, this will be accurate to 13 digits of relative accuracy. This is all happening in MATLAB and Trefethen, actually. So R is, in fact, a function handle in the MATLAB sense, which evaluates a rational approximation. Okay, you can see there are not very many slides. The number there listed is 5, though in fact you can't see that because most of the talk is demos. So I do want to show you something about my main collaborators here. I've listed a number of papers that I personally have a close connection to, but there's actually much more about AAA out there. Many people are using this in directions I don't always understand. These are the ones that I've been most involved with. If you're interested in theory, that's the talk is not about theory. Rational approximation is always difficult from the point of view of theory. We know some things, never enough. But if you are curious about that, then this paper pointed to here is the one which will give you some links to the theoretical set. So you see these 8 guys here, and they're all interesting in different ways. And let me mention 4 of them. So Nakatsukasa and Set were the 2 with which I developed the algorithm initially. And Nakatsukasa is on my hallway. He's my closest colleague at Oxford. Stefano Costa is an extraordinary situation. So he's a guy who lives in Piacenza. And during the pandemic, he sent me some email with some amazing ideas. And we went back and forth and we wrote a paper together, and we have kept communicating all that time. And I never met him until today. And there he is, Stefano Costa. So it's an amazing experience to have a friend that you've never met. Now I have a friend I have met. So it's so Stefano, and in fact, Stefano and Yuji are the 2 with whom I've done the most in this area. And the other person I want to mention is actually a very unhappy story. Peter Badu was an amazing guy who died last week at the age of 29. He was at MIT and he was playing basketball and had a heart attack and was dead an hour later. And this guy was incredible, just an amazingly quick person. I was looking forward to him as really one of my most important colleagues for the next years, and he's gone. It's just amazing. The others are remarkable too, but I won't talk about them especially. Okay, so this is the only slide about how the algorithm works. And in the end, the algorithm is very simple to describe, but it took us months to get there. And along the way, we were trying more complicated things. And you'll never tell from these 2 bullet points, you can't tell how many months of work went into getting just the right algorithm. And yet it works so well. We don't fully understand why it works as well as it does. So the idea is you have some points on the real axis or in the complex plane. This cloud of points suggests that. And you have some data values at the points F. And you want to find a rational function of Z that approximates that data. So the most important thing to know about computing with rational functions, it's a polynomial divided by a polynomial, but you should never use that representation. It's exponentially unstable in a sense I could talk about, but I won't. P over Q, you can't really get anything done with P over Q. And if you go back 30 years to when Dick Varga and his colleagues were working on rational approximation, they were using P over Q, and in order to compute their wonderful results, they had to use 200-digit arithmetic because of these exponential instabilities. Amazingly, there is an alternative, and it's this here. It's called the barycentric representation. So it is a quotient of one thing divided by another, but these are not polynomials. It's a partial fraction in the numerator and another partial fraction in the denominator. This is a stable way to represent rational functions. And it's even stable in the difficult cases where P over Q does not work. So the representation has 2 crucial things. It has the weights, which are these numbers A sub k. And it has the support points, which are these numbers Z sub k. If you look at that quotient, it looks as if it has poles at the points Z sub k, but in fact, that's exactly where it does not have poles. Oops, that's a mistake. Oh, I've lost my cursor. Oh, dear. There we go. So the Z sub k's are the so-called support points. And the denominator has a pole there, but so does the numerator, and they cancel out. So in fact, the quotient takes the value f of z sub k at that support point. So this barocentric representation interpolates your data at m points. But it's not just an interpolant, because it also has these coefficients a sub k. No matter what you choose for those values, so long as they're non-zero, it will always interpolate. So this gives you m additional degrees of freedom, which you can use to approximate. And the way the algorithm works is it builds up a good set of support points as it goes. So here you can see that it's a greedy algorithm. It starts out with one support point and then another until it converges. Each new support point is simply wherever the error is the largest. And then the barocentric weights are computed by solving a linearized least squares problem, which is very easy because it's linear. I say there it's a tall, skinny SVD, and that means typically it might be 1,000 by 30. 1,000 is the number of sample points, and 30 is the degree of your rational function. So you're working with tall, skinny matrices. You can't really see at the bottom, but anyway, as an empirical fact, typically you get within maybe a factor of 10 of the best approximation very quickly and very reliably. I'm going to show now a canned demonstration of how it converges. This is the x-axis going from -1 to 1, and we're approximating e to the x, which is not a difficult problem. And as the algorithm proceeds, the errors decrease rapidly. We've taken 7 steps. Let me say a word about how it did that. So at first, it picks a support point where the error is maximal, and it then takes that. The formula will then interpolate there at the next step. So you see the error is now 0 at the right-hand point. And now we interpolate at the new extreme point. So the error becomes 0 there. So at every step, we're finding the point where the error is maximal, interpolating there, and then at the next step, there's a new point where the error is maximal. Let me say 2 things about this algorithm that are not at all obvious from these pictures. The point that makes it so powerful is not really revealed by this example, because e to the x is too easy. We should have used another function like the square root of x that has a singularity. I was lazy. Because then you would see the support points clustering near the singularity. And that's where the p over q representation is no good. And I forget what the other point I wanted to make is, so I won't make it. Okay, then one more slide before we do the demonstrations. Well, I guess I would say I am learning why rational functions are useful now that we have this tool, and Stefano is teaching me a lot. So every month he comes up with some new thing he can compute with rational functions. It's quite amazing. I advise that you all find Stefano as a colleague. He will accelerate your research. There's a huge field of approximation theory going back a long time, but it's been dominated by theoreticians, especially rational approximation. The strongest people over the years, in the last 50 years, have been the group in Moscow. They're amazing mathematicians, but they're a long way from applications. And what I bring to the table, as I say, is a real interest in numerical computing. That's what I brought to the table until 2018, but now I also bring AAA to the table. So as I say there, one way to view rational functions is that they are like polynomials, except the poles are not all constrained to be at infinity. The poles can be anywhere you like, and that's where the power comes from. So they're a generalization of polynomials. These red words are the names of the codes that I'm about to run. And you can see from the headings on the left, the areas they belong to. I've made a mistake again. And then at the bottom, let me just mention, as I say, the mystery that drives me crazy. So rational approximation is, of course, an optimization. We would like to find the ideal location of the poles to minimize something, and then ideal coefficients. And a priori, it looks like just another optimization problem with all the usual difficulties. If you're close to the optimum, well, Newton's method should converge. But how do you get close to the optimum? And traditionally, that's where the state of the art was. It was another hard optimization problem. But the AAA algorithm does not proceed that way. It doesn't try to satisfy any optimality conditions. It just greedily tries to improve. It has nothing to do with Newton's method. And somehow, we don't fully understand why, it gets around this typical optimization problem of finding the initial guess. It somehow zeroes in on the right territory, even when you start with no information about the problem. I don't fully understand it. It's amazing. And then the mystery that drives me crazy is, it feels as if we now have a magical tool which can solve rational approximation problems. So what about other problems? My prototypical question would be fitting by Gaussians. Suppose you have a function and you want to fit it by Gaussians of unknown width and unknown position. That's another optimization problem. As far as anyone knows, it's pretty hard. In fact, very few people do that with adjustable width because it's too annoying as a problem. Is that really different from rational functions? Or is it just that we haven't found how to vary the AAA algorithm to make it work? I just don't know. So you can see I have deep gaps in my philosophical understanding of why this works as it does. Okay, so the rest of the talk is demonstrations, and sorry to those who are listening online, I will, as always, pass out a handout. Here you are. So maybe some people can share with friends. The reason for giving you a handout, well, one reason is I think it's fun to have a handout and it helps people concentrate and pay attention. Another reason is that I want to emphasize how elementary what I'm doing is given this non-elementary tool. So I'm going to execute these codes. You can see each one is just a few lines of MATLAB or Trefethen. And in each case, I've marked in red the line where we call the AAA. And you can see it's typically just 6 or 10 lines of code. So these are very simple experiments showing the power of these methods. So I'm talking to MATLAB as I do all the time. And the first code is called EXPZ, and I've labeled it warm up just to give you an idea of rational approximation. So if I type warm up, no, that's not the name. If I type EXPZ, let me adjust this a little bit. Okay, so those of you who like to look at code, by all means do. You can see that I have, in this code, sampled the unit disk at 50 points. And then I'm computing the AAA approximation to e to the z on those 50 groups of unity, and also the poles of this rational function. So there they are. You can see 7 poles. That's all you need to get 13 digits of accuracy. Even this problem is surprisingly hard. You know, computing these things was non-trivial until 2018. And the unit disk and e to the z is as simple as it gets. And then every code has some pause statements in it. So in this one, when I press return, I get a sound. Okay, I just pressed return, and now you can see some error contours. So very typically with rational approximation, you approximate on one set where you have 13 digits of accuracy, but then you also get accuracy further away in the complex plane. So in fact, the error contours are 10 to the minus 15, 12, 9, 6, 3, and 0. So even within this big contour, we have 3 digits of accuracy for e to the z. And you can see on the sample points, it's 15 digits of accuracy. So that's the warm-up. I don't mind being interrupted. I'm American, so I like being interrupted. Any questions? Okay. So, well, we've just seen that rational approximation can give you information outside the approximation set. And the next example illustrates that further. It's called gamma plot. So in this case, we just have 30 points on the real axis in the interval from -1 to 1, and we've sampled the gamma function. And when I press return, it will compute the AAA approximation to the gamma function and then plot it. So there it is. The data is just those 30 values. So the data is just here, and yet you can see that it has learned a lot about the gamma function, and rational functions are famous for this, for learning about nearby poles, for example. This pole here at 0 has been captured to full machine precision. The pole at -1 has been captured to about 12 digits, but then we have 3 more poles that are evident, 2 more, I guess. The pole at -2 has been captured to about 4 digits, -3 to about 1 digit. So this is typical rational approximations do something that polynomials can never do. They learn about the function's singularities and even beyond the singularity. Is that the end of that one? Yeah. Any questions? Okay, the next one is called analytic continuation, so zeta fun, and this is for pure mathematicians. So here I've taken the complex plane and the Riemann zeta function, and I've sampled it at 100 points. And as I'm sure you all know, the zeta function is analytic everywhere in the plane except for a pole at 1. But the standard definition of it only converges to with real part bigger than 1. So in fact, if you look at the code, this is just 6 lines. You'll see I've defined zeta by an anonymous function sum of da da da, and that's just adding up the Dirichlet series for the zeta function, 100,000 terms, and that converges perfectly fast if the real part is 4, and here the real part is 4. So I then call the AAA algorithm and plot a so-called phase portrait of the result. So here are the data points again. And then you see this beautiful picture of stripes. At each point, this shows you the complex argument of our rational approximation. So in the right half plane, it's all red. Oops. I'll just redo it. It's the simplest. Okay. In the right, the argument is it's a positive real, basically, so it's red. On the left negative real axis, it's cyan, which corresponds to a negative real result. And then the colors in between are different directions in the complex plane. So if you have an experienced eye, you can get a big sense of the function from this picture. And in particular, these points all along here are zeros on the critical line for the Riemann zeta function. The zeta function would have zeros exactly on the line real part 1/2. Our rational approximation, you can see over on the left, is getting 8 or 10 digits for a lot of those zeros. So it's a pretty accurate approximation in this part of the complex plane. Of course, it then stops being accurate at the left edge of the stripy region. For the zeta function, the stripes would continue forever, but the rational approximation only goes to about the point where the zeta function amplitude is 10 to the 7th. Any questions? Are there any number theorists in the room? No? Okay. MOX doesn't do number theory. If you're curious about the state of the art is the 10 to the 36th zero of the Riemann zeta function. So I'm within a factor of about 10 to the 35 in the state of the art. Okay, next example is called 2 disks. In each one, I've mentioned the name of somebody who has some connection to it. So Alan Turing was the first person who did real numerical computations with the zeta function. Yuji Nakatsukasa, whom I mentioned earlier, is very interested in problems like this one, where you're approximating the sine function, S-I-G-N, sine function. So here we have 50 points on a circle in the left half plane and a circle in the right half plane. And the data values are -1 on the left and +1 on the right. So when we do our approximation, the rational approximation puts a lot of poles between them. The error contours look like that. So you have 15-digit accuracy here and 12 digits and 9 digits, if I've got those levels right. And then you have this numerical branch cut that AAA has put in. Rational functions don't really have branch cuts, but they approximate branch cuts. And if I press return, you see a phase portrait. We're approximating the function that's supposed to be -1 in the left and +1 on the right. And you can see it's accurately achieved that, except on this branch cut region. This is one of the beautiful things about rational functions. They can find or construct branch cuts of complicated functions. Any comments or questions? Yes. I doubt it, Paula.
For example,
Yeah.
let's go for the first that is simple explanation. All the points that we chosen at the beginning are existence, right? And
Yes.
if I don't need anything, also that would be example. Is there any reason?
No, it's just
What happens
simplicity. If I took random points, it would also work fine.
okay.
So in no sense am I trying to optimize points. If, of course, mathematicians always want to optimize things. That's what we do, right? And of course, there would be an optimal set of points which would allow me to have a minimal number of points. And you could put a huge amount of work into optimizing that, but the gain will not be very great. So that would be reducing the number of rows of your matrices. But the savings is only linear. The difference between 500 rows and 100 rows is a factor of 5. That's all.
But if you keep the number
Yeah.
constant,
Yeah.
and you move the point, how the error? So
Well, of course, the error would change a little bit, but it wouldn't change very much so long as you have plenty of points. When we have singularities, it's important to have plenty of sample points near the singularity. And there was another, yes.
This example makes me wonder, what about, I phrase it in this way, maybe extrapolation, or what about your reliability of the approximation far away
Yes.
from your report? Because this is surprisingly, I mean, if it was a polynomial, I would expect to see big errors far
Yes.
away from the circles.
Yeah.
This is not the case. I see larger error in a region where I don't expect.
Yes.
So what, do you have any a posteriori kind of
So-
error estimate?
This is, despite the branch cut, this is a very simple function. And the only reason it's accurate a long way away is that the function is so simple. More generally, you would have some accuracy near the domain, but
Yes, this is a feature of this particular example.
I think so. I have an empirical principle that, roughly speaking, if you have an oscillating function and you try to extrapolate, you can get about 1 wavelength in 16-digit arithmetic, 2 wavelengths in 32-digit arithmetic, 3 wavelengths in 48-digit arithmetic, and so on. But I don't have a theorem to prove that. That's what the experiments show. Here, there's no wavelengths. That's why we get so far. Any other? Yeah. Good question. Yes, that's very ugly, isn't it? So the algorithm does not maintain symmetry. And for example, the first support point will be picked on either that disk or that disk. So even at the first step, the symmetry is broken. Now you can modify the algorithm to impose symmetry. And so you could, for a case like this, you could always pick 2 support points at once. And then of course you will get symmetry. I should mention MathWorks, the company that makes MATLAB, has their so-called RF toolbox, which is radio frequency. Stefano, have you used that? Yeah. And so their code is called Rational, and it's all AAA. So when they learned about AAA, they threw away their previous code and they replaced it. They love AAA. And the reason I mention that now is that they have imposed symmetry. Especially for real functions, it's very disturbing if the upper half plane and the lower half plane aren't symmetric. So they've been more careful. Was there yet another? Yeah.
Probably around the number of poles that you take is related to the number of support points. What about actually the spurious one?
Yeah. Oh, you noticed the spurious one there. You noticed it there. Yeah. So first of all, yes, it is related. So it's one less than the number of support points. So here we have 33 poles, so it must be 34 support points. And yes, that red dot on the left circle is very bad. That is a so-called spurious pole, which will have a residue at the level of machine precision. Now, thanks to Stefano, we have ways of removing those poles, but I'm not going to go into it. But yes, so the two of you have noticed the two most disturbing features of this picture. May I say one more word about this? Paula, when should I finish?
You have 45, 50 minutes, so they take 20, 25 minutes.
Okay. About the curve in that branch cut. Obviously, this can't be the optimal solution. The optimal solution would be symmetric. And this is disturbing to us as mathematicians. We always want the optimal solution. However, you must erase that way of thinking from your head. So this one took 33 poles in order to get a certain accuracy. With the optimal solution, you might do that with only 31 poles. So the difference between optimal and suboptimal is going to be typically a small constant factor, 10, 20%. Of course, sometimes we care about that, but it's not generally the main issue. Let me give an analogy. If you solve a non-symmetric system of equations with an iterative method like conjugate gradients or GN-res or something, nobody asks, have you achieved your accuracy in the theoretically minimal number of steps? That would be an insane question. The point is to get there at a speed that's reasonably close to optimal. So this is analogous here. We're converging to something and we want to do it at a rate that is close to optimal. But whether it's actually optimal is not. Believe me, it's much harder to get the optimal in general. Okay, I should speed up a little bit and switch to number 5 here. And this is something that I just wrote a paper on with Don Huybrechts, with whom I had a wonderful sabbatical this year. It's called equidata. And to this problem, this is a very common problem with a lot of literature. What if you have a smooth function sampled at equally spaced points? How can you interpolate? And the one thing we all know as numerical analysts is that polynomial interpolation is a bad idea. So that's the Runge phenomenon. If you interpolate by polynomials, you get terrible errors. People have devised many methods to fix this, and many of them are good, but as far as we can tell, the best is actually just to fit the data by a AAA approximation. So if we do that here, we get 11 digits of accuracy very easy. Of course, I picked an example where it looks good, and we've studied things more generally, but it does seem that the best method in practice for interpolating equally spaced data is AAA. Next one is called BEAM. So this is for the linear algebra people. This is an example from a standardized test set of examples in model order reduction. And this one is a matrix of dimension 348 that comes from a finite element analysis of the beam, I guess. And what we've plotted here, I'm saying this quickly so some of you will know what I mean and others won't. It's the norm of the resolvent of this matrix on the positive imaginary axis. So these peaks correspond to poles of this system that are close to the imaginary axis. So there's a lot of physics. When I see a tall peak like that, it means the system is not quite unstable, but it's close to unstable. And then the next peak has the second greatest amount of physics in it, and so on. So you have a system of size 348, but it's dominated by a few poles near the imaginary axis. And in model order reduction, we try to find lower degree systems that have similar behavior. So here, all I do is take that function and approximate it by a rational function of degree 20, and with AAA, of course. And you can see that the big peaks are captured beautifully, but some of the low energy structure is not captured. And that's just fine. That's what you want in monomer reduction. Now, I don't know enough about these applications to talk about what role this algorithm really has. I know people are excited about it and they're doing things, but I don't know that stuff. Okay. The next one is called clustering. And this is the application I'm showing you that is closest to explaining a point of theory. The point here is to talk about clustering of poles near singularities and the benefit that brings you. So here, the most important thing in this plot is the X label, square root of n. My cursor is no longer moving. It's hard to use a cursor, I must say, in this environment. Square root of n, we see a straight line on the square root of n scale. So what that corresponds to what we call root exponential convergence, where constant to the minus square root of n type of convergence. And that is the universal behavior that you can always get near branch point singularities with rational approximations. Polynomials have no hope, but rationals can do that. So in this problem, we're actually approximating the square root of x on the interval from 0 to 1. And you're seeing how the approximates converge. If I press return, you see these red dots are the poles of the approximate. And more precisely, it's the degree 20 approximation to the square root of x on 0, 1. The poles are on the negative real axis. And these are the distances of those poles to the origin. And you can see they're spaced out exponentially. And that exponential clustering is what makes rational functions so powerful. And it's also why you have to use the barycentric representation rather than P over Q. And let me just say one more thing, which I won't talk about, but you see they're exponentially spaced, but the spacing is a bit sparser at the left, isn't it? Well, it turns out that's HP mesh refinement. That sparsification is exactly the same factor that you get with HP mesh refinement near a singularity, for sort of the same reasons. And I don't know anything about HP mesh refinement, but I'm sure some of you do. So raise your hand if you've worked on HP. 2, 3, 4 people. Okay. Okay, the next one is called spline nodes. And this is a nice example from Heather Wilbur, who is at Texas, but about to move to the University of Washington. Here we have what looks like a smooth function, but it's not really a smooth function. It's a spline. It's a cubic spline, which means that at the nodes, it has a discontinuous third derivative. Now, you can't see that by eye because your brain doesn't yet have AAA in it, but in a few years, everybody will have AAA in their brains. And then you will be able to see the singularities. Until that happens, we'll do it on the computer. And so I execute AAA and it plots in the complex plane the poles of the rational approximation to this spline function. And you can see the poles are beautifully clustered near the knots. So they are detecting that discontinuous third derivative. It's cool. I really love it. Notice there aren't any poles at x equals 1 or at x equals 9. So AAA has figured out that this spline is not singular at those points. Does anyone know why? If you've ever taught splines in a course, you might know why. I didn't. I was surprised. I had to look it up. Well, it turns out that the standard cubic spline has sort of 2 free parameters. And the standard way that those parameters are used is the so-called not a knot, as Paula is showing us with her hands. So the standard choice is that the penultimate and the second nodes are not nodes. They're just data values. So AAA has figured that out. The next one is called branch cut. Here we have a function that's sampled at 500 random points in a square. And the important thing is that the function is the square root of z minus z squared, which means it has branch point singularities at the bottom left and the bottom right. And when I do AAA, I get a beautiful branch cut connection. And there's a whole theory about this for Pade approximates by Herbert Stahl. And it's everything is known about these curves, these branch cuts that rational approximations approximate. The phase portrait shows you again that the rational approximate has figured out, in some sense, the optimal way to connect that singularity with that singularity. The next example is called extension. So this takes a little bit of talking. This is not the complex plane, it's the real XY. And I have some data, which I'll show you in a minute, inside this starfish region. And I want to extrapolate the data outside. And people are doing this for various reasons in various contexts. I got this example from Anna-Karin Thornberg in Uppsala. Oscar Bruno in Caltech does similar things. But we're going to do this with AAA. So it's not the complex plane, it's just the real plane. So every one of these lines is a separate extrapolation problem. We're doing real analytic continuation in two variables. So I do a different AAA fit on each of these radial lines. So the data look like that. And then when I press return again, it will do these 80 AAA fits and plot the results. So there we go. You can see it has sort of extrapolated the function about one wavelength outside the domain. And we haven't done a serious comparison, but I can tell you that in the picture we model, in the paper we modeled this function. They have a very similar picture, but it only goes about half a wavelength. So I'm guessing that AAA is better than other methods, but I don't have anything firm to tell you on that. Has anyone done things like this? It's done in various contexts, sometimes, usually for PDE, sometimes when they're being solved by integral equations, other times, other methods. But how to handle non-trivial boundaries is always the issue for which people are interested in this. Now, let's see. I have a couple, I guess we're sort of moving into the differential equations territory. The next one is called conf, which stands for conformal. And what this one does is it computes a conformal map from that region on the left to the unit disk. It doesn't use AAA for that, although one could. But once it's got the map, it then represents it by rational functions in that direction and another rational function in that direction. And the red dots show you the poles of those two rational functions. So as far as I can tell numerically, this is the best way to represent conformal maps. It's just so much simpler and faster than using an integral equation and having to evaluate an integral and so on. When I press return, you can see on the left here, it's taken 1 million random points in the disk, and it's mapped them by one rational function back to that domain, and then mapped them by the other rational function back to the disk. And the maximal error was 10 to the minus 5, and it all happened in less than a second. So rational functions give you this wonderful speed and accuracy in representing complicated objects. The next two have a sort of an ODE, PDE flavor. Lorentz refers to the Lorentz equations, and the code has just computed a trajectory of the Lorentz equation. So as you know, that's a system of 3 ODEs, and we've plotted one of them. And then we're going to ask, that's an analytic function of t, but what about the complex t plane? And AAA gives you some idea of the singularities of complex t. And a lot of people have been interested in this. Some believe that this is the right way to understand the Lorentz. I'm not sure I believe that, but it's cool. The next one's called Burgers. This is now a time-dependent PDE, the Burgers equation. I'll run it a couple of times so you can get the idea. That's the initial condition. And then when time goes by, it sharpens up towards a shock, but then it diffuses away because of viscosity. So I'll run that one more time. But then in the right panel, you're seeing poles of AAA approximations. And the point is, it's so simple to do this that you can do it at every time step of a simulation. And notice how the poles come in from infinity and they get near the real axis and then they move out again. And actually a lot is known about that theoretically. It's been proved that there are an infinite number of poles which do exactly this. Now, the last bit of the talk, I'll take another 5 minutes or so. It's okay. This is all about Stefano Costa. So the kinds of things that he first contacted me about involve factoring, using AAA to factor functions on two sides of a contour. And there are many aspects to this. The first demonstration is not very interesting visually, but still I'll show you. There's no buttons to press really. What we have here is a linear Wiener-Hopf problem, where we have the function e to the minus absolute x on the real axis. And our project is to write that as the sum of a function analytic in the upper half plus a function analytic in the lower half. And Stefano's observation was that to do that, we can just approximate the data by AAA. And of course, we'll get some poles in the lower half plane and some poles in the upper half. And now separate those two and use those poles. And now we solve a least squares problem involving those poles. So we set up a matrix and there are two columns for each pole because there's a real and imaginary part. We do backslash least squares. And by doing things like that, we can numerically solve the Wiener-Hopf problem. So I personally haven't really worked on Wiener-Hopf, but this seems promising. And in this particular example, we very quickly got about 10 digits of that. But now I want to show, I'm going to go off piste a little bit and show you a code called Schwartz, because this really emphasizes most the kind of thing that Stefano has proposed. Suppose you have some contour in the complex plane. You could fit a function on the boundary by a rational function. So we have a real function on the boundary and or a complex one, and we fit it by a rational function, and we separate out what's in the inside and what's in the outside. And that turns out to be just a powerful prototypical way of doing many things in complex variables and in at least two-dimensional applications. And of course, there are always implicit branch points, branch cuts going on. Let me show another example. Schwartz stands for the so-called Schwartz function. And the Schwartz function is defined by fitting the function that maps z to the conjugate of z. And I won't tell you why that's interesting, but that's what we're doing here. We're mapping along the boundary, we're mapping each point to its complex conjugate. That's an analytic function on the boundary. And then we're using AAA to extrapolate that in and out. And you can see that invariably there are poles near the bays. You know, here we see poles on that side, here we see poles there. And the steeper the curve, the closer the poles come to the boundary. Let me run one more because I just coded this up this morning, so I like it. Okay, there's another random region. So I can tell looking at the region, this is the sharpest bit, isn't it? So the poles will probably come closest there. Well, it's not that exciting. But anyway, this is a prototype of many things you can do. And I'll finish by showing two such things. The L-shaped region. So here we're trying to solve Laplace's equation in the L-shaped region. We prescribed some boundary data. So Stefano's crazy idea was ignore the fact that you're trying to solve it in the interior. Just fit the data by a rational function on the boundary. So AAA does that very happily. It gets a lot of poles outside and a lot of poles inside, and then throw away the poles on the inside. And now do some linear algebra involving the poles on the outside. And that turns out to give a good distribution of poles to represent the solution you care about. So in this problem, which has a strong singularity there, we've still got 6 digits of accuracy very quickly, as you can see, using this method. And the final example actually isn't so beautiful, but it's in the same vein. It's called wave, but what I'm really doing here is trying to conformally map the two-dimensional domain below that curve onto the lower half plane. Traditionally, for numerical conformal mapping, people write down an integral equation, then they solve the integral equation, and then to evaluate the map, they have to evaluate the integral. And if you want the inverse map, that's a different integral or Newton's map. But here it's just a rational function. So you do AAA, you get poles below and poles above. And Stefano tells us to throw away half of them and then solve a least squares problem involving the other ones. And there's your conformal map. And that is all. Thank you very much. I don't hear anything.
Very much for your very interesting. Is there any question or comment or remark? Fabio, please.
So first, maybe a clarification. I'm not sure I've understood the full algorithm. So you have the sample points and the support points. So the support points is a subset of the sample points that you choose in a greedy way. Okay. Until you achieve the, let's say, the accuracy. So the error when you do this greedy is with respect to the interpolation in the sample point. Is
in all of the
in all of the sample points. So the sample is like the training set, and then you pick up support points in there. Okay. So
I kept saying approximate. I meant to say learn. Excuse me.
So my question is what's so in a way, so how many more sample points you need with respect to the support points, so the degree of the rational approximation?
Well, you certainly want to work with rectangular matrices with more rows than columns. We typically don't worry about that. We take 5 or 10 times as many sample points as support points, and then there's no issue. But following Paula's earlier question, if you want to optimize that and get closer to square matrices, then it becomes more important to distribute the points a little more carefully. And I don't think that's the right way to go. I think that's a distraction that one should avoid. So we would typically have 5 times as many rows as columns. In fact, if you look at these early examples, you notice I only had about 50 points. And normally I would never compute with so many points. The only reason I did that was hoping that you could actually see that they were points, and you can't there. But with Trefethen, I think you could actually see that those are points. In practice, I would have used 3 times as many, but then the figure would not have been as clear.
But it's, well, I mean, in certain applications, you do care about the number of points, evaluating points. If each evaluation is extremely expensive, and you really would like to minimize. So
can I stop there? Where's Francesca? I had a good conversation with her yesterday, and she has an application like that where every row is another Helmholtz solve. So do you work with her? Yeah. Oh, okay. I don't know.
Yeah. So just last question on this point. So yeah, if you do care somehow on the, let's say, minimizing or not oversampling too much, do you have any sort of, or is it possible to get any guarantee that, let's say, 5 times the number of support points is enough for a stable reconstruction or something?
That's a very interesting question. In fact, Toby Driscoll and I are working on that kind of thing. In fact, one of the oddities about AAA is that you start from a discrete set. Why can't you start from a continuum and sample it after? And I think we do know how to do that, and I think we will end up with a guarantee like that, which will be a small number like 3 or 5. But that work is still ongoing.
So thank you. Is there any other question or comment, maybe from home? We cannot see you, so just if you have question or comments, just switch on your microphone. Okay. So if not, we can, thanks again, Nick, very much.
Thank you.
Thank you very much.